And one thing May reminded me to say that we will be sharing the decks of the slides. So there's no need, people in the room, there's no need to take pictures of the screen, although it is okay if you choose to. So it's probably a good idea if you look at the files on your computer as we go along. And we're going to cover sort of what the programs do, how to input data, including how to adjust alkalinity, what's in the output files, and how to understand the results. And the relevant documents, well, the main one is this one called Getting Started with the marine chemistry speciation models. The separate one on alkalinity will also be referred to. Okay, so the three models, the three programs run from the command line on your computer. MCS_C, solutions containing the ions of seawater. MCS_trace, same as the above, plus trace metals, and phosphate and silicate species. And MCS delta, which calculates differences, changes in seawater state parameters caused by a change in solution composition. So how do you use them? Most basically, you put your data in a plain text file called MCS_DAT, or in the case of the Delta program, it has two files, MCS_DAT for sort of solution composition 1, and MCS2.DAT, the second solution composition which it's being compared to. And the MCS trace also uses simply a single MCS_DAT file. So you put your data in the file, you run the appropriate executable, and you view the results in plain text files or comma-separated values. And all of these files are in the same directory. And the calculations can be quite slow, several seconds per composition, and that's mainly due to the uncertainty calculations, which take time. And currently for Windows users only, we do also have a simple Excel spreadsheet way of accessing the or creating the data files. And then you click the appropriate options, and it runs the standalone models for you. And as I say, it's an alternative to working with those text files directly. And if you want to use this Excel front end, that's one of our downloads, MCS_Excel. And there are instructions in the documents directory in there. So you go to the directory that you downloaded in your download with all the files in, and you think, my goodness, that's a lot, and they all seem to have almost the same names. So what are they? The most important are just a handful: MCS_DAT, where you put your data; the executable program, which on a Windows computer will be MCS_C.exe. If it's Linux or Apple, it won't have that extension on it. And then a whole bunch of these files in blue, which are the results files. The files that are all grayed out in this directory, you can forget about those. Do feel free to look at them, but it's probably not a very good idea to change them because the program does read them. So the first of the results files, which actually contains everything, is a good place to start, is the RS1 file, which is what I call verbose output, nicely formatted, all the results. The MCS.RS2 and the comma-separated value equivalent contain just the chemical speciation and activity coefficients. That's the amount contents of every species, the molality, and the activity coefficients. But they're arranged, it's column format, so it'd be easy to read into something else. And the comma-separated value, you just click on that and you go into your spreadsheet program. And the RS3 and RS4 files have columns of the calculated seawater state parameters. The RS3 file, it's all molality-based. The RS4 file is all moles per kilogram of seawater, which is amount content. So that's basically it. This is the data file, MCS DAT. That's the executable. A lot of results files, but everything you can find is in the .rs1. So I'd always look at that one first if you're learning how to use the program. So now let's dig into the data file a little bit. So plain text, no tabs, only spaces. So you want to look at it in a Courier font so that everything lines up. Any line starting with a hash is a comment. So at the top of the file, you'll see there's a whole bunch of instructions which I put as comments. And then below that, you'll see an instruction, enter the type of input composition, which happens to be 3, a salinity here. And then underneath that, some data for 2 solutions, and then a little line saying end of data. And below that, there's actually quite a lot of information, which is other examples of input, which I'll come to a little bit later on. So, as I mentioned at the top, we've got description and instruction in the commented section. And then beneath that, we enter first what type of composition is it going to be. The salinity is always the simple one. 1 means it will be individual species molalities. 2 means it will be individual species amount contents. So in this case, where we've chosen 3, our data consists of a temperature and a practical salinity. That's a calculation. Then underneath, if we're doing 2, just add another one. These are arbitrary values. And you can keep adding numbers and make the file as large as you want. The program will just keep going until it either gets to the end of the file or some line like end of data, or in fact anything that can't be read as a number because it's looking for a temperature. So if you just put any random characters here, it'll stop on those and tell you it couldn't read them. But all of the data above it will have been correctly processed. If you just use that statement end of data, you just get a nice clean ending. That's all. That's kind of the simplest possible example that we can do. I think this just covers what I was saying about end of data. So below that line, you can put anything you want. So it's a good place to put notes, other examples of calculations, and that's what we've done. In fact, all of the calculations that are in the manuals can be found in this section beneath the data in the .dat files. And what I suggest you do today is adapt some of these examples, paste them above that line, and have a go with them. So here's the main results file, the MCS.rs1. And so just going from the top, so this was the first problem process, problem number 1. That was the input temperature. So this is the pressure. So this is the total pressure, meaning it's one atmosphere, so it's sort of sea surface pressure. This is not what is called, I think, a sea pressure, and it's fixed. We don't have pressure variations in the model at the moment. And the section following that, you get all of the speciation and activity coefficients. So here along the top, this is the cation section, hydrogen, sodium, magnesium, calcium. Then the activity coefficients and then the molalities. So the hydrogen ion molality is 6.19 times 10 to the minus 9. And then beneath that, the amount contents, although I used the word molinity just because it's fewer characters. And that is 5.97 times 10 to the minus 9 moles per kilogram of the seawater. So there'll be rows of cations, anions, neutral species up here, which I've removed from this slide. And then the section underneath is the seawater-related quantities. And because we entered a salinity rather than an individual composition, it tells you what the salinity was, 35. And then beneath that, we've got the special quantities and the equilibrium constants, the K star. In the first section, they're on a molality basis. So here we have pH, pHT, total pH, 8.1, and the estimated model uncertainty, then pH on the seawater scale, SW, on the free scale, F, and then PCO2, DIC, alkalinity. And because the DIC and alkalinity are model inputs, that's why it says not applicable for uncertainty, because there is no uncertainty for those, they're defined. Beneath these state parameters are listed all the equilibrium constants, and first they're on a total pH basis, then seawater, then free. And the naming of the symbols you can find in the documentation if you're unsure. And having done all of those on a molality basis, there's a corresponding section underneath that looks exactly like this one, except it will say special quantities and K star amount content basis. So you get all the same numbers as moles per kilogram of seawater, and all the equilibrium constants in the amount content section are as pKs, because that's more commonly used. So I can summarize what's in the other results files fairly simply. MCS.RS2, that's the speciation and activity coefficients in columns. Prefix K to some ion symbol means amount content. Prefix M is molality. Prefix G is activity coefficient. AW is water activity. OSM is osmotic coefficient. MCS.RS4, seawater state parameters and equilibrium constants, molality basis. MCS.RS5, same thing, amount content basis. Comma-separated value versions are exactly the same, but could be read into a spreadsheet program. And all the meanings of the symbols are listed in the appendix for that particular document along the bottom there. So, for example, if you're interested in the molality-based seawater state parameters and equilibrium constants, the first couple of lines will start like this. So you've got I count, which is your problem number. So this is the first problem. Temperature, pressure, pH underscore T, the total pH. U pH underscore T is the uncertainty, and then pH on the seawater scale, and then the uncertainty, and so on. And we just keep going along the line until all the properties of that particular solution are listed. So the second type of, a more flexible type of input is, and a bit more complicated, is where we want to specify individually what the concentrations, amount contents, or molalities of individual ions are. So in this case, let's see, that's actually 2, so that means I think we've selected an amount content, and there's a specific order, which I'll come to, in which the ions must be entered. So we've got hydrogen, which is 0, that's going to be something that's calculated as an output. Sodium, magnesium, calcium, potassium, and so on down through the anions. In terms of acid-base species, kind of any input speciation is okay, because the model is going to calculate the equilibrium. So you could put in all your CO2 as CO2 star, or as carbonate and 2 hydrogens, it would be equivalent. But we are strict about one thing, and that is the input solution has got to be charge balanced and to a fractional precision at 1 part in 10 to the 5. So that's going to make you think about your data. But it is a very handy thing because it traps a lot of silly mistakes. If you've got a very a complex solution, it's very easy not to get the charges, the concentrations right, and the charge balance check is a good test of that. So this is the order in which the ions have to be put in. And here we have, this would be all on one line, temperature, hydrogen, sodium, the cations and so on, then all the anions, and then all the uncharged species. And the grayed out species are ion pairs, which are they're calculated outputs of the model. For input, you just set them to 0. And in the examples in all the downloads, the compositions for seawater in MCS DAT come from Table 4 of the Malero et al. Paper from 2008, where they tabulate these are amount contents down here, and right on the end of the table are all of the molalities. So we work from that reference seawater composition for many of our examples. Okay, we've managed to get to a break without any disasters. I'm not going to make that switch. I was going to do the alkalinity section first. Okay. So what I suggest you do is just spend 5 or 10 minutes having a look at MCS.dat and maybe try running a few cases and make a few mistakes, break the charge balance, see what happens. And if there's anything you haven't understood so far or isn't very clear, ask us some questions. Just say, if you make some of these deliberate mistakes or not deliberate, the worst that's going to happen is the program closes, you're sitting there back at the prompt, and there should be some error message written to the screen, which I hope will explain what the problem was. But if it doesn't, just ask, and I'll do my best to tell you what happened. So we will do some of that. Put your hand up if you want a bit of help, and we'll probably resume with the presentation in 5 or 10 minutes. Okay, everybody, we're going to resume now, please. And what we're going to do is look at how, with the model, we can do calculations for a fixed alkalinity, DIC, and boron and fluorine concentrations. And how to do this is described in one of our supplements called Calculations for Natural Waters of Defined Alkalinity, etc. And the procedure for doing this for a seawater is we start in our examples with compositions of the reference seawater calculated using the values using Malero's tabulation. And then there are a series of actually quite simple steps. It's not as complicated as it looks. We assign the borate anion to boric acid, assign the 2 carbonate anions to CO2 star, replace those anions by OH minus, and then this expression here, just adding these things up, taking off any H plus that we've specified in our solution, we end up with the input hydroxide concentration being the alkalinity. And a simple way of understanding this is to see that the anionic forms of carbonate and borate are replaced by equivalent amounts of OH. You then subtract any free or bound H plus, and charge balance is thus retained. And you've got your alkalinity is the OH minus input, and there it is, all in one number. So if you're working with the MCS.dat file, and you've got one of those long lines of compositions, then what does this look like? So in this column, we've got the species, starting with the cations, the hydrogen, sodium, etc., and the anions, and then the neutral species. So this is like going along one of the lines of input in the MCS.dat file, starting at the beginning and going along to the neutral species. And the salinity 35 seawater, this is the, I think these are all amount contents. This is what you'd find tabulated in the Malero paper. So what we do, we take the bicarbonate amount and the carbonate amount and assign that to the CO2 star, which then becomes our total carbon, because all the carbon is in that one form. And we take the borate anion, which this is the amount in Malero's table, and we assign that to the boric acid. So that becomes our total boron. And then through the keeping the charge balance, the assigned OH goes up from the estimate in Malero's table for what it is in reference seawater to this amount, 2.3 times 10 to the minus 3, and that is the defined alkalinity of the reference seawater for salinity 35. And so you can use as input in the MCS.dat file, you can use the values in this column, and you look at the OH and you say, oh, that's the alkalinity of my solution. And you look at the entry for CO2 star and you say, oh, that's my total dissolved inorganic carbon in the solution. And that's the same for borate, boron, and that's the same for fluoride. So having done that, the obvious question is, well, first of all, how do you change the total dissolved inorganic carbon? Well, you just add or subtract amounts of CO2 star, which is neutral, so you don't have to worry about any charge balance. So just going back, change the DIC, you just change that number and don't worry about anything else. But to change the alkalinity, we do have to worry about charge balance, but it's still pretty simple. If you want to reduce it, that means reducing the OH minus in your input, and you should decrease either, say, sodium, or David tells me that more oceanographically realistic, decrease calcium by the same, the same equivalent amount, and so you retain charge balance. Same if you want to increase alkalinity, just increase that number in the OH column and increase your sodium or your calcium or cation to keep the charge balance. So that's a simple way of doing it. An equivalent way would be to do the opposite thing with H+, but I don't think we need to get into those details. So what are the examples in the MCS.dat file? And I've talked a little bit about those to some individuals, but you'll see the files are actually quite long. So underneath the example at the top, which finishes with that little line, end of data, there's really quite a lot of other information beyond that, which isn't going to get read by the program because it's going to stop before it gets to it, but a handy place to put it. So there are 3 sets of examples, and each of those sets has a header which says example input data and some descriptive information. And there are these 3 sets. The first one is all molality-based compositions. Salinity 35 seawater is the starting point. And there are 4 sets of examples which are used to obtain the results that we show in the manual. So we took the individual species molalities from that Malero paper and then adjusted them as we needed to. And these are followed by a set of compositions that we don't use in the manual, which is just a table of compositions for salinity of 0.1 to 45 that were calculated from those who reference seawater just by adding or subtracting water. So if you want to fiddle around and your salinity of interest isn't salinity 35, you might go to that tabulation and just pull out a line of compositions that's of interest to you. And the second set, which starts with another of these headers example input data, is exactly the same thing, but amount content-based inputs. Solutions are identical to those in the first section. And the last set, same thing again, amount content-based inputs, but we've expressed the input amounts in what I've just been describing, which is where CO2 star is the dissolved inorganic carbon total, and the listed value for OH minus is the alkalinity. So if you're going to be playing with some numbers, it's probably you're going to want to look at this last, that should be 3, not 2. You probably want to look at this last set and pull out some examples of a suitable salinity from the table at the end, going from salinity 0.1 to up to 45. And that's the sort of arrangement that we have in all of the MCS.dat files for the 3 different programs. We put in the body of the file all the examples that we've run and put results for in the manual. So at this point, before we move on to one of the other models, David is going to show how to use a simple Excel front end. This is for Windows users, for how to generate the input for the MCS _C program. So it generates this front end, generates a data file, and then using batch files, it calls the model and pulls out the results. So I'll hand over to David.
Okay, thank you, Simon. You who are remote can't see me. My name's David Turner, and I'll change from this into Excel, and I've seen that some of you here in the room have managed to load the system up, and it works by clicking on buttons and filling in numbers. And the buttons are numbered so that you've got 3 choices. The beginning here, marked number 1. The simple option that Simon showed is reference seawater. So if you click on there, you've got a space where you can put in temperatures in Celsius and salinities. And I'm only going to put 1 in because everything takes a little time. You just put in a number in each one. One thing I'll show you as well, if you put in a ridiculous number, which is out of range, when you press all data entered, you'll get some little messages in red telling you that salinity has to be between 1 and 45. You can't have 150. But all you do then is say, OK, correct that, and press the all data entered again. Now it's happy. And it tells you to go to the command prompt and run a batch file. Now, in the instructions that I sent out, I explained in Windows 10 how to get a command prompt down on the taskbar here, which is in the correct directory. Windows 11 seems to be not quite so simple. I did have a try with Windows 11 in Spanish a few minutes ago, and I didn't get very far. I don't understand Windows 11 yet. our university has a managed computer system. They haven't given us 11 yet. But what I have here is I have a command prompt that's in the correct one, and you'll see if we go back here, it says enter the command c.bat. So we do that, and then this actually then starts moving files around, and we'll get the calculation system working. Okay, it tells you now that a total of 1 problems have been done. So then we go back to Excel, and you have to be very careful. You don't be too enthusiastic and press calculation complete until it really is complete. Otherwise, you'll find yourself looking at old data files, and then it will get upset because it's trying to overwrite a file that's open. So wait until it's finished there, press calculation complete, and then you can open results files. So there's one which is the individual species, and this is one of the files that Simon showed you, is in Excel, comma separated format. So that one is there, and also the one with the state variables. So they're there, and you can take out the results you're interested in, put them somewhere else, because of course, next time you run the program, these files will be overwritten. So always remember to take them with you, take the data out. The other thing is, before you do anything else, close those files, don't leave them open. Now, one of the things with this, you don't, with this program, as far as I've managed to work out with my tests, if you want to do something else, you don't have to close it and restart it. If you press another button numbered 1, then it'll start again from scratch. What I'll do as well is show you what you can do with a non-standard composition, or at least put your own composition in. So if you click on that one, you've got a different window where you can put in the amount contents of everything. As it says on the top, it's amount content only. You can't use molalities in this, and it just does the one. Now what I've done here, I've actually got the standard seawater composition put out ready in Excel format here. I feel a bit like one of these DIY programs, you know, so this is one I prepared ready earlier. So what I'm going to do is just paste that in. Put in a temperature, whatever. Before I run it, one thing, you can just press all data entered, and you'll go back and it will tell you what to do. However, I will show you what happens if you don't balance the charge. So say I put in the chloride content wrong, all data entered. What it does, you've got a charge imbalance. And you can actually get it adjusted automatically. You can choose to adjust either chloride or sodium so that the charge comes back in balance. Since I messed up chloride, I'll choose chloride, make changes, and then it shows you what it's done there. Then you can do next, and you come back again, and it tells you to go and run c.bat again. and that will run away and go off in the same way as before, so that when it's finished, you go back to the Excel and you can open the results files in the same way. So that's another way for those of you who have access to Windows. That's an alternative way of putting in the data, and it does as well mean that if you're putting in your own composition, then it won't let you put in a composition which isn't charge balanced. It simply objects. I don't know how it's going with Windows 11 over there, whether you've achieved any more success yet. Yeah. But so this works reasonably well automatically. We do have to go back via the command prompt, because if I try and run everything from Excel, Excel thinks that everything is done and finished as soon as it's loaded the command prompt. So there seems to be no way around that, because it's running a program at one remove. But I'll leave that there for the moment. As you can see, there are some other options there that correspond to the other programs that Simon will describe. So what we'll do, when Simon's described those programs, I will show how it works in the Excel system for those that have Windows. So I'll hand back to Simon.
Right. Thanks, David. So I should say, before I move to the next slide, is everybody okay, or are they in the middle of trying the Excel? Get your hand up if you want a few extra minutes, seconds. No? I think we're okay. So the next thing I want to describe is what I call the difference, or the delta model, which is calculating changes in seawater properties caused by a change in solution composition. So this model deals with, or has the same species available as before, the species present in reference seawater, same types of input and output, except now we've got two input files. One is mcs.dat for the initial composition, solution 1, and then mcs_2.dat for the second composition, the one we're comparing it with. And you can have an indefinite number of these pairs of solutions. I mean, let's say you had 100 pairs. The first of those, each of those pairs would be listed in mcs.dat, the second of each pair in mcs_2.dat, and the program would go through reading the pairs from the two data files and calculating the differences in the seawater state and other parameters between them. So all the output files are the same, except with the addition of one, which is mcs_delta, which lists the changes in the seawater state parameters and their estimated uncertainties. And you might say, well, what's the point of going to the trouble of a special program for this? I could just run mcs_c twice, one for one set of compositions, one for another, and then just subtracted the two. The reason for doing it is because you can't, if you want the uncertainties in this difference are not simply additions or divisions or subtractions. They're rather more complicated than that, and that's why we put it in one program. So what's a typical use? Let's say we have a natural water that corresponds broadly to a seawater composition of some salinity, but with some alterations to the major ions, enough that we're concerned that the acid-base equilibrium, the equilibrium constants for the carbonate system, for example, might be different from what they are in a straightforward seawater. So the approach is to put the seawater salinity, our initial solution, in MCS.dat, and enter the altered composition in MCS_2.dat, then run MCS_delta, and then we can retrieve the change in pK or other property from MCS_delta.res. So, I mean, a good use of this, if you were interested in, I think, the best accuracy, would be to calculate, let's say, a pK, if it's an equilibrium constant you want to know, calculate the pK in the seawater of the known salinity using, say, CO2cis, and then the pK, our estimate of the pK in this natural water that's slightly different will be equal to the CO2cis value plus the delta pK that we calculate using MarChemSpec. A couple of notes, few notes. MarChemSpec is likely to calculate the difference property. I've missed a word there. The difference in the property more accurately than the absolute values, which is a good thing. MCS estimates the uncertainty in all these changes, as well as those of each of the properties of the two individual solutions, and those can be found in the other results files that we already know about. And the inputs in the two files, data files, I mean, they can be salinities or moralities or amount contents. It's up to you. So let's look at the list of files in the main directory. And those for solution 1 are exactly the same as we have for the ordinary MCS C program. So the grayed out ones we don't need to worry about. MCS.dat, where we put the composition, the bunch of results files, and the executable itself. But now, in the same directory, there are the files that correspond to the second solution, MCS_2.dat, and the associated results files for the properties of that solution, and then also MCS_delta, which is the differences in the seawater state properties. And as a reminder, the RS1 file, verbose output, all results, RS2 file, speciation and activity coefficients, RS4 and RS5, the seawater state parameters. So, the rogue yellow box at the top. So typical input, MCS.dat. Here we've entered, let's see, 3 for the input composition type. So it's a salinity. We've got 2 25 degrees centigrade, salinity 35 solutions. And in MCS_2.dat, what we're comparing them with is, I think these are molalities. These are the 2 sets of input compositions. They both got the same sodium. The magnesium is different. The calcium, let's see, that's the seawater value. That's changed in the second solution. So there are some alterations. There's some alterations here. So we're comparing, this solution with the first one here, and the second solution in MCS2.dat with the second solution in MCS.dat. So the only results file we really need to describe is the only one that's different from MCS the _C case. And this is the _delta.res file, which tells you the changes in all of these properties. So starting on the left here, I count is the problem number or the solution number, and all of these properties are for the first solution. And then on this side, we've got everything, all the changes on a molality basis. On this side, on an amount content basis. And you see that all of these equilibrium constants on the amount content side, there is pKs here. And if you look closely at the results, there's something that might cause a bit of head scratching at first. You see the DIC and total alkalinity on a molality basis, there are some very small changes, and they are very small, down at the 10 to the minus 10 level. But we didn't change in the input solutions either of those things. So why would we see that? And the answer is because the difference in those two solutions, the degree of dissociation of water changed, and that changed, therefore, the total amount of water present. And since these are all molalities per kilogram of water, all of the concentrations change by some tiny amount, which is vastly below what you'd ever be able to measure, but it is there, and you see it in the model. And if you then look across the same numbers for amount content, you might scratch your head even more and say, well, now these, although they're very small at the 10 to the minus 6 level, they're 4 orders of magnitude more than they were for the molality case. Now, how could that possibly be? And the answer is that in these, when changing the composition of these solutions, we were swapping out on a mole-for-mole basis one ion for another, or we were adding a small amount of extra salt. So on an amount content basis, we were changing the total mass of the solution that was present. And that's why on a per kilogram basis, the DIC and the total alkalinity have changed, even though the actual moles of total carbon haven't changed in the solution that we were modeling. So it's you have to be a little bit careful when you're thinking about these concentration scales. So what have we got at the end of these two files in the distribution, the two data files? So it's the same as I described for MCS_C. 3 sets of examples. Each one begins with a text example input data and some descriptive information. And for simplicity, all of the initial solutions, which we're comparing with in MCS.dat, are just salinity 35 seawater. And it's the final solutions in MCS_2.dat that are different. So the examples that we have are salinity 35 seawater, but with doubled sulfate, and I think additional magnesium to balance it, and 2 salinity 35 solutions with alkalinity reduced and then increased relative to normal seawater, and then 2 other solutions, first with extra total carbon added, and second with sodium carbonate added, which are two slightly different forms. So in this first section, it was all molalities. In the second section, it's all amount contents. In the third section, it's exactly the same as the second section, but all the seawater components, the inputs are such that the OH minus value is the alkalinity, and the dissolved CO2 value is the DIC, and the same thing for borate. So you can play around with those numbers in your tests and trials. So now it's time, I think, for David to come forward again, and he'll show you the Excel approach to doing one of these calculations.
Okay, thanks, Simon. I'll go back to Excel here a moment. The heading for this one is modified reference seawater. In other words, the Excel system is set up so that you start with the standard reference seawater, but can make changes to it and look at what happens there. So if you click on this one, you now get some different things here. You put in a salinity, and then you select the components you're going to change. You can change 1 or 2, and you get a drop-down box here And you'll see that your options, you can change the neutral inputs, which are carbon and boron. They're put in as neutral species, and so they don't affect the charge balance. If you put interchange alkalinity, you can balance it either with calcium or with sodium. Again, making sure the charges are balanced. And if you want to change any other components, then you change one of the salts in seawater. And I've put a selection of salts there. Again, this is the need to keep the charge balanced. So that, I think the example I put in the notes, if I remember correctly, was looking at the effect of dissolving a certain amount of calcium carbonate in the water, which you can do here. So if you take alkalinity balanced against calcium, and when you select one, a second drop-down box comes. If you just want to change one thing, just carry on then. You ignore the second one. But if we're going to look at that process, you put carbon as well to be changed. And then you click on number 2. You're happy you've done that. And you've got a space here. Put in a temperature. Now what it does here is you see the standard values of the alkalinity and DIC that are in the reference seawater. So we can, for example, we can put in an alkalinity increase of 10 micromoles here. And if this is calcium carbonate, then we only want to add 5 micromoles of carbon so that we have the correct balance for calcium carbonate. And then, when we're happy, press all data entered and go to the command prompt. And now we put in a different batch file. So one of the things to be careful of with this is that when you go into the command prompt, have it very clear in your mind which batch file you're going to run. Otherwise, you might get a result which surprises you. So we go in there and set that running, which will take a little while. This isn't the world's fastest computer to do the two, but we'll get a result from that in a moment. So you can see, although some things are easier to do in this, you become, because it starts with reference seawater, you become a little limited in the sorts of things that you can do. But I think this is quite useful for being able to explore what happens if you start making changes to the standard seawater. Okay, so now it's run that. So we say calculation complete. And with the files you can open, at the moment, I only have, for the individual species of state variables, I only have the standard seawater. But as Simon said, the important one here is the differences. Now, this is a text file. It's not in Excel, but if you click on there, then you see that the text file comes up in Notepad. And so here now you see for what we've done, the changes that happen here and the uncertainties so if you look at the total pH, we've got about 0.0064 change in the pH here. But the uncertainty is pretty small, and this is one of the things Simon was pointing out, that the uncertainties are rather small, because you'll see the uncertainties for the individual pH measurements are much larger. You'll see that when I show the MATLAB example. But again, I mean, this is not directly in Excel, but you can always, of course, copy and paste any results you're interested in for further use. And as usual, make sure you take out of the files, copy out the information you need before you do something else, because they'll get overwritten, and do close all the results files before you try and do anything else. But I'll leave that there for now. So those of you with Windows, that's another way of doing things. And we'll now actually have a break until we move on to trace metals.
Yes. 5 or so minutes if anyone wants to try this. And then I should say, so what we're going to do afterwards is there'll be a kind of similar presentation to this one on the difference program, but just for trace metals, and David will do a little demonstration. And I think we'll have a break when I encourage you to get up and demolish the fruit and the cookies that are at the back. And then after that, we'll deal with we'll cover the MATLAB and the Python functions, which should take less time. It's not going to be won't be a huge presentation. So I'll just give you a few minutes before we resume. Okay, everybody. The last bit of presentation on the standalone models covers the calculation of inorganic complexation of a series of GEOTRACES trace metals, which are listed along here. 1, 2, 3, 4, 5, 6, 10 metals, plus, if you wish to add them, the minor species phosphate and the 3 related species and this silicate species. So the chemical system that the model is treating is the species of reference seawater, which we've already covered, plus the extra metals, plus the complexes, which happens to be a round number of 100 total species. Of the same input file, or the same named input file, mcs.dat, as for the other versions of the program. And there's one extra output file in addition to the .rs1 and so on, and that's mcs_trace.res, which lists the fractional speciation of each trace metal present, both free and complexed by each of the ligands. And I'll show you an example of that. So the simplest possible use case is we want an estimate of the fractional speciation of the trace metals in the seawater of the specified salinity and temperature. This seawater has the properties of the reference seawater, with et al. Again, just with water or added, removed to change the salinity. So all we have to do is put the salinity and the temperature in mcs.dat, as we have in some of the other versions of the program. But in this case, the program ncs_trace will automatically add a very small amount of each trace metal as a chloride salt, but it's too small to have an effect on anything else. And the speciation can be found in the usual output files, and we can retrieve the fractional speciation, the summary, if you like, from mcs_trace.res. There are no estimates of uncertainty for this. I mean, the major reason really is that the data for trace metal composition on which the model is based is relatively sparse. I mean, much more sparse than it is for the ions for acid-base equilibria in seawater solutions. the measurements of trace metal complexation involve many assumptions, even for much simpler solutions in seawater. So any except the sort of grossest estimates of uncertainty would likely be fictions. So we have not tried to delve into that mess, at least not yet. So the sets of files, this is starting to look a bit familiar now. The grayed out ones that you don't need to bother with. The mcs.dat, where you put your input data. The executable, that should be trace, not there, not C, pardon me. The usual output files here, and mcs_trace, which gives you the fractional speciation as before. So let's have a look at an example result, which is actually pretty simple, doesn't require a great deal of explanation. So this is the content of an mcs_trace.res file. On the left, again, the I-count values, that's the problem number 1. And then a list of all of these, of all of the metals, of which this is only a fraction. And across here, the fractional speciation. So to just take the top one, aluminium. Free fraction is about 4.4 times 10 to the minus 10, so hardly anything. The fraction of aluminium as a hydroxide complex is virtually everything, and there's a tiny amount of fluoride complex too. Going down to cobalt, most of it is free, 0.8, fraction of 0.86. Most of the rest is as a carbonate complex, and there's a small amount of hydroxide complex there. And let's see, iron 3, everybody's friend, almost all of it has hydroxide complex, and a very tiny fraction has the free amount. So the general case, where you want to, where you have a sort of arbitrary speciation rather than a seawater composition, it starts to get a little bit complicated just because there are many more species than in the other models. So let's say we want an estimate of the speciation for one or more trace metals in a natural water of arbitrary composition. So in mcs.dat, we enter the modalities or amount contents as before, seawater species, the same as for the other programs and in the same order. And the trace metals we'd simply generally put in as total, total values, maybe balanced by chloride, and set all the complexes to 0 because the model is going to calculate them. And we'd run mcs_trace, and the speciation can be found in the usual files, and we retrieve the fractional speciation as I just showed. Now, the issue is that there's 100 species here, so some care needs to be taken in order to get the order right. Otherwise, you could just end up in a mess. So you'll find this table in the manual, and what it is just reading left to right. It's a list of all of the species that you'd need to put or specify on one line of input. So the highlighted yellow are all of the seawater species in the usual order. You'd start at the beginning of your line of input with temperature, then hydrogen ion, sodium, magnesium, so on to the end of the cations. Then after that in red are all our trace metals, and then the rest in black over the next 2 lines are all the cation complexes that can form. And then starting here, species number 40, that's chloride, followed by the other seawater species. Then species 49, the next few, phosphate, hydrogen phosphate, dihydrogen phosphate, and the silicate species here, followed by a bunch of anionic complexes. And then species 70 is the first of the uncharged seawater species, boric acid. Then the CO2 star or DIC, HF and some ion pairs, 2 more phosphate and silicate species, and then a whole bunch of uncharged complexes, which in your input file, input line of data, you'd simply set to 0. So the only other things to say really about the trace metal calculations are to refer to the manual. So there's a table in the appendix which lists a set of individual modalities you could put into MCS.dat to do the calculation that I showed, giving you the fractional speciation in salinity 35 seawater. And some of the other tables document a full list of species names, because we had to be a bit careful about those, because we don't want to use a name in a column header that might be misinterpreted by a spreadsheet or other program as something else. So I was trying to avoid parentheses in names. So this is iron 2 hydroxide. You see the square bracket there, which is FeOH3 minus, and SiOOH3 is in reality this anion here. Another thing, if you're looking at output, and if you're looking at the not the comma separated values output, but the RS2 file, because there are 100 species, one line of output occupies about 4,500 columns, so you're going to need a fairly manly text editor to cope with that. Otherwise, you're going to get lines wrapped or possibly truncated. I don't know. Just something to be aware of. So what did we put in the example MCS.dat file? The usual format, 3 sets of examples. In the first case, salinity 35 seawater, trace metals are automatically added by the program. In the second example, species modalities from this table in the manual. And in the third example, 6 different compositions, but ones in which we change the DIC and the alkalinity while having those trace metal species present, so you can see how these sort of seawater changes affect the speciation of the complexation of the trace metals. The second of these sections, again, same heading, same as the above, everything expressed as amount contents. Third section, same as the above, but all of the seawater components are expressed so that OH minus is equivalent to alkalinity and CO2 is DIC. So it's that last section that might be the best one for you to play with and try some calculations. So at this point, I mean, I think that's all I need to say about the trace metal case. So David, you want to take over?
Okay, and back to Excel. To get the trace metals, if you click on reference seawater, because it calculates these from this Excel system at the moment, just in reference seawater, you just click add trace elements, and as before, you can put in lots of temperatures and salinities. I'll only put in 1 because we don't want to wait for ages. Click on all data entered, and then now it tells you to run trace.bat. And so we put that in and wait for it to finish. I realized sitting down that there was one thing I didn't say about using the Excel for a composition that you yourself put in. If you have a system and you don't want to include, say, bromide and fluoride, put in 0 and that's fine. Don't leave the spaces blank because it will complain at you and say it's got a non-numeric character. So it runs perfectly well without all the components there, but you must make sure you put in 0s for anything that's missing. Okay, so that's complete now. And again, calculation complete, and you get the same results as normal, but then this trace metal summary comes as a text file that Simon mentioned. Now, one thing I should say for those that are used to ion pairing models of these trace metals, you may well have noticed by now that for the transition elements here, there aren't any chloride or sulfate complexes. The reason is that weak interactions like the transition metal cations with chloride and sulfate are actually much better treated as just ionic interactions in the Pitzer model rather than complex formation. And not only that, there's a great deal more information about the thermodynamics of those interactions than there is about actual stoichiometric constants, which are quite limited. So that there are good descriptions over the whole temperature range for those interactions. So things look a little different for that reason, so that actually those interactions are pretty well treated. On the other hand, the hydrolysis of these metals is less certain, and carbonate complexation, which is often the most important, is even less certain. In many cases, there aren't many good measurements. Copper is the only one that I would say has pretty reliable measurements of the complexation constant, and it's the only one for which there is any information on the temperature dependence. I've actually applied the same temperature dependence across the board to all of them in the hope that it's better than not putting anything in. But that's the reality we're in at the moment. There are quite a lot of uncertainties in these trace metals. Okay, I'll stop there. And that's the end of the Excel. There is a close button here, and it's much simpler to stop it by pressing that, and it just closes the file. If you try and just close it using the normal red cross, it'll start telling you that it's a read-only file, you can't save changes, and so you have to click around a bit more. So use the close button. Okay.
All right. Thank you, David. I'll just say two things. The Python and MATLAB presentation will begin, well, relatively shortly. It will be mercifully rather shorter than for the standalone programs. But first, as long as May has brought her phone, we're going to have a picture, aren't we, May? Hey? Okay. Let's gather around our MarChemSpec logo.